Okay, this is the seventh and final video for Chapter 23 on geometric optics. In this last video, we take a look at what are called lens systems. So a combination of two or more lenses that work in conjunction to provide some final image that has a certain set of properties that might not be able to be obtained from just a single lens alone. So we have quite a bit more versatility when we start to combine lenses. So in this video, we're going to take a look at, or maybe I should say focus, on a few applications of lens systems. So we'll end the video by looking at the common microscope and telescope, but I want to start with the human eye. Now, out of our five senses, I've read some reports about what percentage of information comes from the visual sense as opposed to the other four senses, and it's hard to track down exactly the number, but I've read some estimates that somewhere between 80 to 85% of all input to our brain comes from the visual sense. So again, sort of hard to come up with hard data on that, but certainly the eyesight is a very important part of our world. Well, let's take a look at how the eye uses a combination of lenses to be able to achieve the all-important goal of being able to see objects that are both near and far, and it does so by relying on a series of optical instruments that are located in the front portion of our eye. Let's take a look at the anatomy here. Light entering the eye is refracted most by the outer cornea. So this cornea is somewhat fixed in shape. It doesn't really change much throughout our life. But it does have a very strong refractive index. It's able to focus light quite a bit. But it isn't able to sort of change much in response to both near and far objects. So we have further focusing power in more like fine-tune adjustments of refraction by the lens, and that's located right behind that. So the lens has a couple of muscles attached to it. Those muscles push or pull on that lens to either make it thicker or thinner, which sort of changes the overall focusing power of the combination so that we can see images from objects that are both near and far. And of course, the image is a real image that's projected onto the back of our eye. It is a real inverted image focused on the retina. Now, if you have poor vision, then you know that the actual image that is created on your retina is blurry, and so everything seems to be sort of blurry on the edges. So if you haven't had corrective lenses, then you might not appreciate how important a corrective lens is to be able to see the fine details. Or abnormalities and how they are corrected. Let's take a look at this. Sometimes people are farsighted, which means they can see distant objects, but they can't see things up close. So perhaps you're in the back of the classroom, you can read the board just fine, but if you're trying to read from a textbook, you have a hard time focusing on things that are close. So farsighted, often called hyperopia, is an affliction that prevents us from seeing things up close. This is corrected with a converging lens. Let's see why that is. Distant objects are able to focus on the retina, but close objects focus behind the retina, so it's shown by this picture here. So when I have an object up close and the light rays are sort of diverging quite a bit here, we rely on the cornea and lens combination to try to create a crisp image on our retina, but we simply do not have enough focusing power to bend those light rays enough when they're up close to be able to get them to focus on the retina. So we need to have another converging lens that sort of increases the focusing power of these two devices that normally work by themselves. So we have an extra converging lens there to increase the focusing power. Effectively, the eye is too short, or what happens is oftentimes as people age is the muscles that control that lens are not quite strong enough to make the adjustments necessary to focus that where it needs to be. So we need to rely on some external lens to be able to help us there. Now, if we are nearsighted, that would mean that we can see things up close, like for example reading from a textbook, but we can't see maybe the board from the back of the classroom. So this is called myopia. In contrast to hyperopia, we correct this with a diverging lens. When we're looking at distant objects, the light rays are more parallel, and when our lens cornea combination tries to focus that light, it would focus in front of the retina. So close objects are focused on the retina, but distant objects focus in front of the retina. So we use a diverging lens to sort of spread that light out a little bit prior to it entering our eye, and that allows us to sort of shift that focus back onto our retina. Effectively, the eye might be too long, or the maximum focal length of the lens is too small. Now, if you go to a optometrist or an ophthalmologist to have your eyes checked, oftentimes they will prescribe a certain lens of a certain power. So let's take a look at how we might measure the power of a lens. It is equal to the reciprocal of the focal length of that lens, measured in meters. We often use the term the diopter to describe the power of the lens, and it is measured actually in inverse meters. So that should make sense. If it's a really strong lens, that means it's going to have a really big effect on either maybe converging, trying to get those light rays to converge at a much shorter distance. And so we'd have a small focal length, and if I take the reciprocal of a small focal length, I'd get a big diopter value. So the bigger the diopter, the stronger that lens would be. Okay, so let's take a look at a combination of lenses in more detail. The eye is, of course, a good example of a lens combination, where we use multiple lenses or refractive devices to create a final image. In lens combinations, the image of one lens becomes the object for the next lens. It is possible to have negative object distances. We'll see that in an example down the road. If you recall from our machines labs, a compound machine consisted of two machines or three machines interconnected, where the output of one became the input to the next machine. Very similar to here, how a lens might create an image from this particular object. Well, that image now serves as the object for the next lens in sequence. So we could have any combination of lenses that sort of work in conjunction, where the image created from one sort of serves as the object for the next lens, and so forth. So very similar to machines in that regard. Now, the magnification of the final image is the product of the magnification of each lens separately. This result was certainly put into practical use with the compound microscope and the telescope, where oftentimes we need to get a very large magnification that cannot be done, at least practically, by a single lens alone. And this is a common feature of the compound machines as well, where we have the mechanical advantage of one machine is sort of multiplied by the mechanical advantage of the next machine in order for us to get some very large mechanical advantages. Similarly, we rely on the product of the magnifications of these lenses to create a very large or very magnified image as well. Okay, so let's take a look now at the compound microscope and the refracting telescope in a little bit more detail. Both of these devices use a combination of two converging lenses, but where we place the lens in relation to the object is different because of the purpose of each of these devices being slightly different. One is to view up close objects and get a really magnified view of an object that's relatively close to the device. Another is to view an object that's really far away. So it's going to use a series of two converging lenses. We just locate the lenses at different locations based on the application that we're looking at. So let's take a look at the microscope first. The microscope, probably used in your biology class to view some specimen that you placed on maybe a glass slide. You place that relatively closely to the objective lens. So the slide is placed just outside of the objective's focal point, thereby creating a real, inverted, and enlarged image for the eyepiece. So this would be, let's see if we go back to our cases, if we're just outside the focal point, I believe that was called case 4. Okay, so that was where the object was located just outside of that focal point. Creates a real, inverted, and enlarged image over here. Now that serves as the object for this eyepiece. The image is located just inside of the eyepiece's focal point. So that would be, let's see, just inside of that would be case 6 here. So what that's going to do is it's going to create an enlarged but virtual final image of this of this object here. And so what we end up seeing is a much larger view of that object. It would be virtual, so it's actually located over here, and this is what we're actually viewing. Okay, so it's using a combination of two lenses placed in the appropriate location so that we can look at a relatively close object and provide more detail than we can do with just our eye alone. Now if we take a look at the telescope, we are intending to look at very distant objects and still want to be able to get a nice up-close view. So now what we have is a little bit more of parallel light rays coming in, goes through the objective. The objective is going to create some sort of real image over here, and we place that image just, again, inside of the eyepiece's focal point. Okay, so the object is at infinity, so a point image is created at the focal point of the objective lens. Okay, so this object here would actually be at the focal point of this, and I locate that just inside the focal point of the eyepiece. The reason for that is that the image then that's located just inside of the eyepiece will create an enlarged virtual final image of that distant object as we view here. Okay, so again, very similar to what we have up here, except because we're viewing a very distant object, we sort of put this in case number 1, where I have a very, very far object, parallel light rays coming in, creates an image at the focal point. We locate that just inside the eyepiece's focal point so that we can use case 6, again, to be able to view an enlarged virtual image of that object. So there we go, a couple of optical instruments that you've probably used at some point in your life, how it uses a combination of lens systems to achieve a particular goal. Now in this last slide or two, we take a look at a few numerical examples where I show you how we might apply some of the principles that we've been studying in theory, how we might put them into practical use. So let's try this one here. A -3 diopter lens is located 25 centimeters in front of an 8.0 diopter lens. An object is 1 meter in front of the positive lens. What's the location of the final image relative to that positive lens, and where would the image be if it was not for the diverging lens? So quite a few things going on here. A sketch would certainly be useful. So let's go ahead and draw sort of our optical bench here. So we have a -3 diopter lens. That would be a diverging lens. So it looks like this. And so since its power is -3.5, we could think of its focal length as 1 over that, and so that would be a focal length of -0.286 meters. Okay, so that would be the focal length of that lens. It is located 25 centimeters in front of an 8.0 diopter lens. So I'm probably going to need to use color coding here, so let's go ahead and put this in like so. So that one has a power of 8.0, so its focal length, again, the reciprocal of that would be 0.125 meters, and this would be positive. Okay, and so let's put some numbers up here. These two are 25 centimeters apart. Okay, and we have an object that's 1 meter in front of the positive lens. So we can take some object out here, and boy, a lot of numbers here, so the sketch is imperative here. Let's keep our units straight. So these are in meters. We're going to make that be a 0.25 meter distance. And let's make this be a total of 1.0 meters all the way to here. And of course we might also want to put this in here as a distance of, let's see, 0.75 meters. Okay, so just some basic math there to be able to come up with those distances. Let's see, what is the location of the final image relative to the positive lens? So the light source, let's go ahead and just draw some rays here. The rays like so are going to be spread out a little bit before they before they are focused by this converging lens. Okay, so these light rays, I'm just going to draw a couple of them, and I'm not going to use the ray diagrams to be able to do this, but these light rays will be spread out some. Okay, and so this will then focus at some sort of image over here, and again, I'm not going to do the ray diagrams to be able to do this, but that's where our final image would be. So let's see if we can't figure out where that's going to be by using a series of two lenses. Let's first create the virtual image for this diverging lens. So I'm going to use blue here. I'm going to try to find where this thing is located, the image of this, and I know it's going to be somewhere up here. It's going to be smaller in size, and it's going to be closer to that lens, and I know that from my case studies for diverging lenses. So let's see if I can't find this distance. So let's call that di. So 1 over di is equal to 1 over f minus 1 over do. And so 1 over a negative 0.286 meters minus 1 over 0.75 meters. That will give me for that 1 over di is equal to a negative 4.83 inverse meters. So that means that di would be equal to the reciprocal of that, which would be a negative 0.207 meters. Okay, so the negative is important. That means that it's located in front of that lens, 0.207 meters. So let's go ahead and put that down here. Okay, 0.207. Now, pretty important here for the converging lens. The converging lens is actually viewing this as the object, right? So I need that distance. So I'm going to go ahead and put this down as DO for that lens, and that value. Let's see some basic arithmetic here. Since this is 0.25 and this is 0.207, I get about 0.457 meters for the distance for that object. So let's go ahead and use green for this one. I'm going to find di here. So 1 over di is equal to 1 over f minus 1 over do. And so 1 over that focal point, our focal length is 0.125 meters minus 1 over the 0.457 meters. And that will give me for di, I'm just going to go ahead and write to that final answer, of 0.172 meters. Okay, so that would be the distance to the image for this thing here. So let's go ahead and put that up here, 0.172 meters. Okay, and so that would be where the final image is created. Now what's interesting is to see where would that image be located if there was no diverging lens here. So let's just see where the image would have been without that additional lens. So I'm just going to use black here for this one. The distance that the object is away from here, DO, would be 1.0 meters. Okay, so that's without that lens there. This converging lens would be viewing just this. Okay, and F again is still the 0.125 meters. So if I wanted to find DI using this case, it'd just be the same math that we did before, with just some different numbers. So 1 over 0.125 meters minus 1 over 1. So there we go. And so DI there would be about 0.143 meters. Okay, so that's where the image would have been created if it wasn't for that divergent lens. So that would have been over here somewhere, and it would have been a little bit closer. I don't quite know how big it would be. I didn't do any magnification values here, but clearly the effect of that diverging lens was to sort of shift the ventral focus a little bit further back. Now, this could actually be a scenario of myopia that we're trying to correct. So maybe without the diverging lens, we would get the image focused in front of the retina. So we use the diverging lens to sort of create an image that's further back. Okay, so that sort of matches the way that we might correct a myopic vision. Okay, and so now finally the last example for all of chapter 23. For this example, I'm going to sort of combine a lot of ideas here. I'm going to sort of treat you like you might be a practicing optometrist or maybe a ophthalmologist. In one of the tasks that you would complete here is to try to correct a person's vision that is coming in and complaining that everything seems to be a little bit fuzzy as they view maybe distant objects. So let's see if we can't use this as sort of a case study for what ophthalmologists or optometrists might do in practice. Now certainly the science that optometrists and ophthalmologists must undertake is more than we can do in an introductory physics course, but hopefully this will give you an example of how we might rely on basic physics principles of refraction, Snell's law, and geometric optics that an optometrist or an ophthalmologist might have to be able to do as part of their normal work. So a typical human eye is about 22 millimeters in length from outer cornea to retina. Let's assume the person is myopic, so they are nearsighted. When they view a distant object 3 meters away, they see that it's actually focusing at a distance of 21.3 millimeters instead of the 22 millimeters that we would desire for it to be on the retina. Now certainly this number is made up here. The optometrist or the ophthalmologist would not necessarily know that it focuses at that point, but they do know that the person is complaining of a fuzzy image, and so based on the fact that they're having a hard time seeing something from a distance away, they would recognize that this is myopia. Okay, so it clearly is focusing in front. So let's see if we can't just figure out what the power of the uncorrected cornea lens combination is to begin with, and then we're going to try to design a corrective lens that would be located in front of their eye that can sort of fix that vision for them. Okay, so a lot going on here. Let's go ahead and take this one piece at a time. So first part is to find the power of the cornea lens combination. So to do that, I'm just going to recognize that the power is equal to the reciprocal of the focal length measured in meters there. And since we're given the distance of the image and the distance of the object, this is a relatively straightforward calculation. And so I just can plug in these numbers here. The image distance is 21.3 millimeters away. I'm going to go ahead and put that in meters to keep everything sort of consistent units here. So 0.0213 meters plus the object distance is a 3 meter distance there. So 1 over f will be equal to about 47.282 inverse meters, which means the focal length would be just the reciprocal of that, 0.02115 meters. Now, power is just the reciprocal of the focal length, so really this is the power in diopters. Okay, and so we might say that that is 47.3 diopters. Okay, so that's our first little problem. Now, as you'll see, 47.3 diopters is actually a very strong lens. So what that means is that the light is bent quite a bit by this cornea lens combination. Let's see if we can't figure out what kind of lens we're going to use to try to correct this vision. So let's go ahead and draw some ray diagrams here. This is a distant object coming from 3 meters away, so the light rays are almost parallel. Okay, and they're going to be bent by the cornea, bent more by the lens, and they are, of course, focusing in front of the retina. So this distance here, let's go ahead and just draw that as 21.3 millimeters. That's a little bit too short, right? We need to sort of spread that light out a little bit before it gets so that we can focus it back here further. So you may have guessed here that we're going to end up using a diverging lens. So the next part of this is assuming a corrective lens can be placed 3 centimeters in front, what type of lens should be used? Well, we're going to have to sort of spread that light out some before it enters the eye. Okay, so if I were to trace now the path of light coming from that distant object, comes in, it's going to bend a little bit away from the center of the eye here, and now this is going to end up bending that, and when we bend it, we should be able to get it to sort of focus further back. So this light now will be coming out, bending a little bit away, and then coming in and focusing back there. So our eventual distance that we want, the distance to the image after it's been corrected, we want it to be a full 22 millimeters. Right, so we're going to try to do that using a combination of lenses. One somewhat fixed. Right, we have the cornea lens combination here. It's somewhat fixed at the 47.3 diopter value. Now we just need to determine what we place in front of this so that we can sort of shift the entire thing back. Okay, that's the idea behind it. Now, this is still going to be a little bit complicated. In order for us to figure this out, I'm going to try to treat the cornea lens as a fixed power and figure out how far away the object should be, such that when I use that power and the required image distance, I can sort of figure out what DO needs to be. Now granted, the actual object is 3 meters away, but I want to be able to determine where this lens will create a new image that's a little bit closer. So that's really what I'm looking for, is where do I have to place or how strong of a lens do I need in order to bring that distant object a little bit closer so the eye can view it more easily. That's the idea. So first thing I'm going to do is I'm going to try to figure out what is the new DO for the cornea lens using the power to be 47.3 and DI to be 22.0 millimeters. So I'm going to use the same kind of equation. I'm just going to try to solve for a different thing. So I'm looking for 1 over DO is equal to 1 over F minus 1 over DI. Now in this case, 1 over F, well, I'm going to go ahead and just write 1 over F as a 47.282. Let's go ahead and just do that, make it a little bit simpler for me here. So 1 over the focal length of the cornea lens combination. Well, that's 47.282 inverse meters, minus now 1 over DI. Well, DI for this is going to be now a 1 over 0.022 meters, and so now I can find DO is just a reciprocal of this. Let's go ahead and see what that is. And as I do all those calculations, I see that the distance to the object really needs to be 0.547 meters. So what I effectively have to do with this lens is I have to take something that's 3 meters away and try to bring it so that it's actually quite a bit closer, right? A distance of 0.547 meters, not 3 meters. Okay, so the eye now would be sort of focusing on a virtual image that's brought closer because of that diverging lens. Okay, so now that we have that, we can sort of figure out the power of this lens. I'm going to switch colors here. I'm going to go ahead and make this be orange, so we might be able to have a better chance of keeping track of the math as we go through this. So all of the calculations now for the diverging lens is going to be done in orange down here. So let's see. I have 1 over F is what I'm looking for that. I know that the distance to the image is going to end up being, let's see, 54.7 centimeters or 0.547 meters in front of this. So I need to subtract 3 centimeters. Right? This is actually 3 centimeters in front here. So if I want to get this distance, it's going to be 0.547 minus 0.03 meters. Okay, and so that would be about equal to 0.517 meters. That would be DI. Now, I do need to be careful here. DI would have to be a negative here. So when I put in 1 over DI plus 1 over DO, that 50.517 meters actually has to go in as a negative. Okay, plus 1 over DO. Well, the object for this is actually 2.97 meters away, right? Remember, this is a 3 centimeter in front of the eye here, so the object is actually 2.97 meters away, and so now I can find 1 over f quite easily there. Let's take a moment here to do that. And I see as I was going through my calculations, I forgot to put that negative right in there, so I'm going to do that here. When I do the math correctly, I get that 1 over the focal length is a negative 1.6 inverse meters. And so the focal length for that, if I take the reciprocal, I'd see that the focal length then would be a negative 0.626 or so meters. Now, this right here, again, would represent the power of that diverging lens. So the power to correct that vision would be a negative 1.6 diopters. And with everything else being the same, that person's eye that's able to not able to bend the light, or rather I should say bending the light too much so it focuses in front of the retina. Now with that new diverging lens placed in front, sort of spreads that light out a little bit before entering the cornea lens combination, and sure enough, that should sort of shift that focus back, and that person can now see that distant object more clearly. So there we go. The last example for you, definitely a challenging question. Hopefully, if you've been sort of keeping up with the material over the course of the entire chapter, hopefully this last example was something that you could follow along. So there we go. That completes chapter 23.